All right, good morning, everybody. All right, so we are going to spend the last 3 regular lectures going over some a little more advanced data structures, but also with an eye on your future courses in algorithms. What we're going to learn about today is a data structure called a Bloom filter. And the idea behind a Bloom filter is allows us to be able to significantly reduce memory to be able to look up and check whether or not we have something in a table. So it uses a lot of hash table ideas, but the thing is, for the first time, we're going to trade off accuracy in order to do this. And the idea that we're going to investigate that you'll learn a lot more about when you go into the algorithms course is what is known as a heuristic. So far in data structures, everything that we have done has given us an exact result. It's been deterministic. I want to look up a key in a hash table, I can find it. If I want to be able to look up an element in a display tree, I can find it and display it to the element, or if it's not in there, we find the closest element and display it up there. Reallocating double the previous memory for a dynamic array. I have all these examples of going into exact results. Breadth first search, depth first search, minimum spanning trees. All of these things have given us an exact result. And all the problems that we've worked on are where we're looking for an exact result. We're trying to find, for example, the longest increasing subsequence. We still eventually are going to come up with some sort of exact number. And even the random number generator in SRAND, which we used most recently to be able to develop randomized probabilities for a tree, is dependent upon the equation and the current clock in the computing device, which is why we call it a pseudo random number generator. So all of these things are going into an exact solution. However, what happens when we don't need an exact answer? You know, sometimes you just need it to be close enough. A lot of algorithms try to get into this area of, if I have it just close enough, that's a good enough solution for me to be able to do the things that I need to do. In this case, we first encounter this idea of Bloom filters in 1970 at back then it was called the Computer Usage Company, very innovative name, very creative. And the whole idea behind Computer Usage Company is that they are trying to learn how to verify elements in the dictionary. So we're starting to put computers together, eventually building towards ARPANET and the internet, and we want to be able to verify if we have certain malicious strings or certain inputs. However, as more and more information is out there, it becomes impossible for us to be able to store a local copy of the internet on our own laptops. So we have to be able to come up with other ways in order to be able to verify whether or not something is malicious. So if we had all of these elements and all this memory, we'd still have to look through every single element in the characters of these arrays, right? So if I'm looking for a malicious URL, I have to check every single character in the URL. And even if I store it in a hash, which is even more of a trade-off of memory, it still takes a significant amount of time and incurs a lot of memory space. So the question is, well, how could I potentially verify that I want to do this? So if we're using a hash table, the other one thing I wanted to point out is that if we're trying to keep track of millions or even billions of strings, and we have reached the size of the capacity of the hash, we have to rehash. So potentially we have to rehash billions of elements, which can take a significant amount of time. All of this exactness adds complexity, and all of this exactness adds memory. So the question is, what if we don't need to be exact? What if I can get a really close enough percentage of accuracy, but if I can trade off a lot of this memory and time that I'm incurring, I would really like to get rid of that. So the idea behind a heuristic algorithm is that it's designed to solve a problem in a faster and more efficient manner than traditional methods, but the trade-offs are for optimality. It may not be the fastest or the most accurate, but there's something that we are gaining with that accuracy and speed that's prohibitive. In the case of the Bloom filter, when they were inventing it, the prohibitive aspect is too much memory. We have way too much memory for us to be able to do this task, and it's not really helping us in order to solve this problem. So sometimes you don't need an exact answer, and so think like Eliza Hamilton. If you can get 97.8% accuracy, but you can get a 99% reduction in memory, that would be enough. You don't have to go all the way there. So let's reduce all the way from strings down to their fundamental units. Let's go all the way down to bits. And we're going to learn about a C++ container called a bitset. And the bitset forms one of the foundations of the Bloom filter, the other of which are going to be hash functions. The idea behind a bitset is it's an array of bits. So if you have a bool, you have one bool. And if you were to just say standard vector of bool, you would be able to put in bits and push them back and be able to create a set of elements and then be able to access them. So bit sets are going to allow us to be able to do the exact same thing. And now a crucial aspect of how this is going to help us is that the capacity of the array is 2 to the power of the length. So if I have 5 elements, I can still represent 32 values. And instead of having to represent each of those 32 values, I could have some sort of way of saying, all right, I can just store 5 bits, and if it's true or false, I can look that up. So here I give the example 2 to the 8 is 128. So first thing I'd like to do is I'd like to go through 3 common interview questions that use bit sets to show you the benefits of using bit sets. And then we're going to dive into this idea of Bloom filters to see how it is that we can identify, as an example, malicious URLs. So the first problem we're going to do is what's known as the subset sum. And you're given an array, and so in the example, it's 4, 1, 10, 8, and 5. And a number of queries where each query we have to check whether or not a subset whose sum is equal to the given number. So in this case, one subset could be 1, 5, and 10, which will give us 16. So 16 should return a result. However, 7 should return false because there's no subset sum of those values that sums up to 7, excuse me. So as a result, we should be able to do this, but we want to reduce this idea of big O of n time for each query. Because if I wanted to go through and say, well, how would I figure out, I'm sorry, this is going to be big O n squared. If I would have to say 4 plus 1 plus 10 plus 5 plus 8, I'd have to figure out some way to be able to check every single combination of sums, and that would be big O of n squared time, which is a brute force approach. So first thing I'd like to do is I'd like to show you an approach for using what are known as bit sets to do so. So what we're going to do is we are going to, and first let me bring up subset sum. And what I'm going to do is I'm going to scroll down to main first, because I want to show you how it's initialized, because it has a unique quirk to them that's really important. Okay, so, okay, good. So in main, I've created an array of numbers. It's the exact example from the slides. And then I have a const int max sum. Bitset templates, but it templates to a number. So it's a little quirky, and it has to be constant. It cannot be a variable. Also, you can't just put in 25. So here I have a maximum sum, that I put in, and that gives me a bit sum of 29 bits. So normally, if we were designing a class, what we may choose to do is we would say, all right, I have some sort of vector of bits underneath, and then in my constructor, I would pass along a number of bits, and then that constructor would be the size of the vector, and then we would say it'd be 0. So if we were designing it, we might choose it like that. But in this case, the way that the C++ container is designed is that we have to put it in as a variable like so. Does that make sense to everybody? Let me check the chat because that can be a little confusing to people the first time they see it. So now what I'm going to do is I'm going to print the initial array of bits, and then I'm going to call a subset sum algorithm. And what this is going to do is it's going to allow me to do bit shifts. So how many of you are currently taking logic design? Okay, almost all of you. And how many are you familiar with bit shifts now and the idea of logic design? You can move things over. So we're really going to take advantage of bit shifts here in order to be able to get our subset sum in a very efficient way. So let me go back to the slide. And what we're going to do, our trick is we're going to initialize 0 to be bit 1. Because what if we're going to assume that our sum, if we add none of them, the sum will be 0. And also in this case, we're going to assume that they're all positive numbers, so we're not going to have any negative number type issues that will come up. So if I want to say, well, the first element is 4, 4 plus 0 is 4, correct? So what do you think I would want to do to the bit set here? Give me an idea of what we might want to do to simplify this. This is going to be potentially 29. So we summed all of them up, and the largest possible number is 29. That's where I got 29 from. I apologize. That should be clear. So I can represent 0. I can represent the sum of 7. I can represent 28. So what do you think I might want to do just with the bit shift? So I know the number is 4. What can I potentially do here? So I'll give you a hint. That's representing 4. Yes. What's that? Get rid of the padded zeros. I'm not quite clear what you mean. Just throwing ideas at. All right. Well, that's fine. We're gonna get rid of 1 0. Okay. So we want to make this a 1. So we see that? So now if I have 4 and 1, what are my potential sums? Right now I have 3 potential sums. If I have 4 and 1, what are the 3 potential sums? Yes. 1, 4, and 5. Very good. So you have 1, 4, and 5. So here it would be 5. So what I would do is I'd say, well, I'm going to set that bit to 1, and now I'm going to bit shift all the other existing bits. So I'm going to shift by 1. So it's going to happen the first time I'm going to say, let's shift by 4 here. So I'm going to shift by 1 now, all of them, and this will actually add everything. So this will be 4, and this will become 1 and 5. All right, so let me check the chat. Very good, so 5. So now if I have 4 and 1, let's do 4, 1, 5, and 3. So if we're taking this approach, what do you think we want to do now? I have all the actual subset sums, so now we're using dynamic programming. Yes. Very good. So here we would have 3, and here we're shifting 0 to the right by 3. We're going to shift 1 to the right by 3. Then we're going to shift 3 to, oh, so we're going to leave 3 alone, my apologies. We're going to shift 4 to the right by 3. And then we're going to shift 5 to the right by 3. So that gives us 7 and 8. Is that making sense? So let me walk through the animation so I can make it clearer. So what's going to happen is, well, first let me show you the code. So this piece of code here is the crucial piece of code. And what's going on there is I have the old value of the bits, and I'm going to say, give me the value there, which will be 3, and then bit shift it and OR it. So if I have 0, 0 for an OR, okay, everybody knows the OR logic. So that means if it's already 1, leave it be. Otherwise, if it's 0, we're going to update it to 1. So that's where the bit shift OR equals bit sums shifted by that number. So let's walk through this and we'll see everything here. So initially, we're going to say array nums is equal to 4, which means that we're going to shift the current value by 4 and then OR it with the original bit sum, with Bitsets. So now what happens is I'm going to take 1. So the initial one was 0 and 4. So now we shift by 1 and we get 1 and 5. Does everybody see that? And then we OR them, so now we've updated that result. And so now 2 is 10. So we're going to shift it by 10 and then update all those values as well. Then we're going to have 8. We bit shift the whole thing by 8 and then OR it. And we see how all these values are getting updated. Every single one that's true now is a subset sum. And so now what I'd like to do is I'd like to show you the actual code here. So this is the subset sums. And in order to get a bit set to work, you have to template it. Here we have size t bit set size. And what's going to happen is first I'm going to say bit sums.reset, that puts everything to 0. And then I'm going to set the initial bit to 1. Then I'm going to show the initial, I'm going to print them all out, so I would iterate through and print everything. So in each iteration, what I'm going to do is I'm going to say, give me the specific array, bit shift all of them by that specific number, and then OR it with the previous bit sum. And then I'm going to print out the result. So what we're going to see is after I go through everything, it's going to have that specific updated value. So what I would like to do is I'm going to compile it, subset sums. I'm going to show you the first part of the output run. So that's the second part of the output run. So here after inserting 0, we see that the first bit is 0 and all of them are 1. So we have 4. Then we do 1 and we see that 1 and 4 plus 1 is 5. So we have that. Then we put in 3 and all the values are updated. So we put in 10. We see all those values are updated. Then we put in 8 and then 5. And so if we calculated the result correctly, in this case it's 29, or the sum of all of them, then 0 should be 1 here because that worked. And then the final value should also be 1. So we have all the elements in there. And every single bit that's there is printed out, and every single bit that's 1 is an actual subset sum. Does everybody see that? So we're able to significantly reduce the amount of time of looking it up once we get a request. So then what's going to happen is I'm going to, sorry, let me scroll down here, check values. So bit set If it's less than 0, so here I'm just checking to make sure that we don't put an incorrect value, or if it's greater than bitset size, it's not valued either. Otherwise, what I'm going to do is I'm going to say, well, if that value is true, then I'm going to print out the result that it is a subset sum. Otherwise, I'm going to say that it's false. The last thing I do is just a little thing to kind of help you visualize the solution. I have this function called print bitcheck. And what it's going to do is it's going to pass that value that we're checking, and it's going to put 2 stars around that particular bit. So we can see exactly which one we looked up. So in this case, I checked subset of 2 does not exist. And then it calls that print bit check, and we see that the stars are around 0. So that's the one that we checked, and we know that's not a subset sum. And here we have 5, that one is found, then 6. We knew initially that 7 should give us 0, and it does. 16 is correct, 24 is correct, 28 is correct, and then I put in 43, and it said, well, 43 is bigger than a possible sum, so it's not going to work. All right, does anybody have any questions about that? Let me check the chat as well. We're checking. The next problem I want to show you is what's known as finding the Hamming weight of an unsigned integer. A Hamming weight is the number of 1 bits that we want to look up. So you're given some sort of unsigned integer, and what we need to do is we need to say, all right, how many 1 bits are in this unsigned int? Now we know that the unsigned integer is represented underneath as a binary value of 32 bits. However, when we define it as an unsigned integer, it prints it out in the integer representation that we're familiar with. So what we're going to do is we're going to use this idea of a bit set, and we're going to keep track of what our output is and what that binary representation will be. So what I'm going to do is I'm going to set an unsigned int called mask to 1. And what this means is that I have a 1 bit, and if I shift it left, that's going to become 1, 0. If I shift it left, again, it's going to be 1, 0, 0. Does everybody see that? So my goal is I'm going to go through and I'm going to check every single bit, and I'm going to use an AND operation to do so. And the clever thing about what C++ does is that when I say 2 values AND, if I have an unsigned integer that I'm checking and an unsigned int mask, if it returns 0, that means every single bit didn't match. So if I put in a mask of 1, and I keep bit shifting it over, if the 1 lines up with a 0, it will return false. If it lines up with a 1, it's going to return true. So this allows us to be able to just do 32 iterations and then get the exact number. And so this particular program, hammingdistance.cpp, forgive me, let me scroll down to the actual algorithm. So this is the algorithm get Hamming distance. So in the get Hamming distance, I read in an unsigned int num, and this is the number that I want to see how many 1 bits. And then I also call a bit set by reference. This allows me to store the results so I can actually print out the representation of this number. So I have an unsigned int bit, an unsigned int num bits, because I'm going to keep track of the number of bits, because this is ultimately what the problem was. And then the other thing is I'm creating this mask and I'm setting it equal to 1. So what's going to happen is I'm going to iterate through, and I'm going to say while, sorry, I'm going to do a for loop, but for unsigned int is equal to 0, it's going to be less than bit set size. In this case, because I'm templating it, I've thought ahead, and I've made it 32. And then I'm going to increment I. And so the first crucial line is this line of code that I've highlighted. I'm going to zoom in those a little bit so it's clear. If, let's say I have, let's say this was 5 bits, right? And I want to see how, if I have 1, 1, 0, 1, 0. And initially, I'm going to say that mask is 1. So mask is going to look like this. And it's going to say if num and mask does not equal 0, well, now it's going to check every single one, and. So if the unsigned int that's returning is 0, that means we didn't catch it. Does that make sense? So now what's going to happen is I'm going to go down, I'm going to show you what's going to happen after the if statement. After the if statement, I'm going to bit shift mask by 1. So now if I have that 1, 1, 0, 1, 0, I will bit shift, so now it becomes 0, 1, 0, 0, 0. And then if I AND them all, what's going to happen is it's going to go 0, 0, 0, 1, 0, which will return 2. Which means that now we're going to go inside and say num bits plus plus. So now I have found a 1 bit. And then I want to explain this line of code, but I have the comments there, so if you want to review it there. The bit sets will go from 0 to maximum, just like we want them to. However, it's going to go like this, with the least significant bit on the left. The reason I have 31 minus 1 there is because when I print it out, I want to put in our results in a direction that you're used to reading them. Does that make sense? So basically, I'm just doing it to flip it. So if I had 1, 1, 0, 1, 0, what would happen is, if I was trying to representing it with just I, it would come out as 1, 0, was it 0, 1, 0, 1, 1. Does everybody see the difference there? So I'm just doing that 32 minus 1 to make it legible in what you're used to. So in print bit set, I'm going to print out all of the bits in that bit set. And then in main, what I'm going to do is I'm just going to call all of these values, and here I have the largest possible unsigned int value, and 4, which is as small as it gets. I could put in 0 and it will work. But here I'll say the number of 1 bits in num test, and then we'll print the actual results. So I'm going to run the Hamming distance, give Hamming difference, will return the number of bits, and then it's going to print out the actual bit representation. Does that make sense? So let me run that compilation. And so what's going to happen is I have the number of 1 bits in 4 is 1. And if it goes like this, you're going to see that it's 1, 0, 0 at the end. If I say it's 7, we see that it's 3 1 bits, and we have them all here. 31 is 5, which is what we should expect. 32 is 1, and we get 1 and then 5 zeros. 42 is 3, 1, 0, 1, 0, 1, 0. And then it should test it out all the way out to the largest possible value. So now what I'd like to do is, I want you to kind of think, just take a guess. We have all the pieces together, so here's another common interview question. Give an unsigned integer, reverse the bits, and print the result. Print the numeric value. What do you think we should do here? Any ideas? I'll give you a hint. I was dropping a big hint about it when I was telling you about that 31 minus 1 and how it changes it. What do you think we should do? Any ideas? Anyone in the chat? Anyone? No idea. No idea how to reverse bits. So if I give you, yes. Yeah, so what we're going to do in reverse bits, there we go, is that when I run the algorithm, we're going to essentially do the same thing. And then instead of 31 minus I, I'm just going to do I. And then I'm going to have an unsigned int reverse result, where I'm just going to say unsigned int power 2 to the 31 minus I. Yes. No, because we need to check every single possible value. So the thing is, okay, so the question is, can we just swap them? The issue is that it's given to us as an unsigned integer. Not as a, if it was a bit set, it would be pretty easy to just do swaps. But since it's given to us as an unsigned integer, we actually have to go through and perform this task all 32 times. So I like the innovation there, but the issue is that it's given to us. Are there any other questions? So here, let me just walk through what our approach will be. And here we'd say, well, I'm going to iterate through all of them. I'm going to perform that mask. I'm going to do the bit shifting of the mask every single time. And if it's 0, instead of 31 minus 1, I'm just going to 31 minus I, I'm just going to do I. And so that'll give it me in the opposite order. And then I'm just going to plus equals a reverse result to return. So if it's going to be here, if I'm at I, right? I is equal to 0. Let me give you an example here. So let me do 1, 0, 1, 1, 0, right? So if here it's going to be 0, but if here will be 1, I would put 1 here, and let's say that this is going to be 5. So this would be 5 minus 1. So this would be 2 to the 4, 2 to the 3. So this would become 4. So that becomes 8. Right? So that'll eventually become 8 plus 4 plus 1. So we're going to reverse those values and get that result. And then test is the exact same. And then when I run that, I'm going to run make reverse bits. And then here I have the reverse of 4, right? We're going to have, yeah, it's going to be 536 million. And we see that the first 3 bits are 0, 0, 1. Does everybody see that? So that allows us to see that we can reverse it. And then we have all these values. We see 1, 1, 1 is 7, 31 should be 5 ones, 32, 0, 0, 0, 0, 0, 1. So we're seeing that it's successfully reversing it. And then if our test works properly, if we get in the largest possible value that's all ones, it should also produce all ones and give us the exact same number, which it does. All right, so now what I want to do is let's take this understanding of bit sets and combine them into what's known as a Bloom filter. A Bloom filter is a bit set that has 2 or more hash functions, and we put in an input and we use those values inside the bit sets to indicate whether or not we have an element in that particular bit set. So it's like a hash function, except instead of storing the element, all we're doing is storing a bit. So the goal there is to reduce a significant amount of memory use. So for example, let's say I had 7 elements, right? And then I have, and the hash is x mod 7. If we were doing this as a linear probe, we would store, if I had 23, I would say that's 2, and I would store 23 there. But instead, I would just be updating that to 1. So we see that? And if I had 20, now the thing with the Bloom filter is it's going to have multiple hash functions. So if I do x divided by 7 mod 7, 23 divided by 7, we would say it's 3. And then 3 mod 7 is going to be 3. So the whole idea is we're going to update every single bit that corresponds to a particular input. So the more bits we have and the more hash functions, the more accurately we can represent results. So here in this diagram, X, Y, and Z are hash functions. And when W comes in, the way we can verify if an element is in the Bloom filter is that we then say, is this element in the Bloom filter? And then we run it through all 3 hash functions. And if all 3 return true, then we can say that the element is in the Bloom filter. Does that make sense? So I'm going to run through a couple examples to provide a little more clarity. But the first thing I want to address is an issue with Bloom filters. The issue with Bloom filters is that they can potentially give you false positives. If you have a bunch of elements in the Bloom filter and you put in a number that's not in there, some sort of value that's not in there, and all the hash functions return true, it's going to return that's there. So this is where we kind of tie back into this idea of a heuristic. A heuristic is mostly accurate to some sort of quantifiable level. I can say that it's 96.5% accurate, and the issue is, are the inaccuracies something that I can do? So let's take for the case of malicious URLs. For a malicious URL, if I return a false positive, that means that approximately 3% of the time in a particular Bloom filter, I'm just coming off the top of my head, approximately 3% of the time, I would get an inaccurate result where I falsely say that the URL is malicious. However, the trade-off is every single time that something is a malicious URL, it will produce a positive value. I will get false positives, but I will not get false negatives. Does that make sense? So all I would do is if I had this case, a very small percent of the time, I would get some sort of complaint from somebody who runs that website and say, hey, I promise I'm not a bot. Please let people use my website. Then you have to come up with some sort of way of finding exceptions. But but what you're not letting through is you're not letting through malicious URLs that you know to be bad. So, and that gives you a preview of heuristics. That's something that you'll go into a lot more detail when you get into algorithms. The other benefit is I can store all these values with a significant improvement in memory. So if I design my Bloom filter good enough, so if I have, let's say I have 4 hash functions and a sufficient number of bits, and we'll go into those calculations in a moment. If I have a sufficient number of bits and I have a sufficient number of hash functions, I can save a significant amount of memory with a very small trade-off in accuracy. The other thing is no deletion. So just like a normal hash function, we would have to do some kind of lazy delete. Now with Bitsets, if we have the list of elements saved somewhere, we could just call that refresh method that I called earlier. Remember when I first called the Bitset and I said set it all to 0, then we could just perform all the elements for our Bloom filter. In the event that we needed to, let me say that somebody who's running a website got their act together and now it's not a malicious website anymore. We take that out of our list, we put everything in the Bloom filter, and then when our tool that is catching malicious websites, it only needs to check the Bloom filter, and it allows it to run much faster. So the first thing I'd like to do before I show you a code example is I'm going to show you the equation that we use to determine how many bits that we should put into our Bloom filter. And the way we do this is we have some sort of desired error rate. So this would be an error rate that we have calculated to say that this is okay, this is an acceptable error rate, and the number of elements. So the number of elements that we anticipate that we would need to be able to represent with the Bloom filter. In order to calculate the number of hash functions, we say the negative log base 2 of the error rate. So if we said, for example, 0.125 is our acceptable error rate, then this is going to return 3. Then what I do is I have the number of hash functions and the number of bits that the number of elements that I need to represent divided by the natural log of 2. That will give me the total number of bits that I need to have in my Bloom filter. So 2 major equations. You need to know how to calculate the number of hash functions. K equals negative log base 2 of E. And then M is K, the number of hash functions, times the number of elements we need to represent, divided by the natural log of 2. So you can probably guess that you'll be permitted to use a calculator on the fly. All right, so what I would like to do is I want to quickly take you through I want to design a hash function. With these particular constraints. So we're given we want to design a Bloom filter where we have 2 hash functions. And we're going to show the results of our hash function after we first put in 2 elements, 129 and 479. And then we're going to check to see if 129 and 123 are in the Bloom filter. So first I know that I have 2 hash functions. And I think I left out of my problem statement that our error rate is 0.25%. So our desired error rate is 0.25%, and we have 2 hash functions. So since I have 2, I realized what I did now. Since I have 2 hash functions, I was able to reverse engineer it. The reason we have 2 hash functions is because since we have 0.25%, and we put that in log negative, that will return 2. From there, we know the number of elements, and what I've done is I've said 479 times the number of hash functions 2 divided by the natural log of 2. Now in an exam problem, and you'll see it in the homework assignment, I'm much more explicit about the error rate and the number of elements that are needed. So I would say, given a number of elements, M equals whatever, and I would say an error rate, determine the number of hash functions and the number of bits that we need to be represented in the Bloom filter. But here what I've done is I've done 2 times 479 divided by the natural log of 2, and we have 1,382 bits. Now let me bring up a calculator real quick because I want to show you something, which is actually going to be, first I need to prove I can spell calculator. There we go. And so what I'd like to show you here is if I had 479 and I'm multiplying this by the number of bits in a signed integer. So that is 15,000 328. That would be the number of bits to store everything. And in fact, let me make this 480 because I want to be able to represent 0. 480 times 32. So 15,360. If I do 1 over, and I multiply this by 1382, and that's the number of bits that we have in our Bloom filter, that's only 8.99%. We have gained a 91% improvement in our memory that would be required to verify 480 integers with a trade-off of 0.25% accuracy. So that's the benefit there of the Bloom filter. Right, so here what I have is I just have a simple representation of bits. And so what I would do with K1 is I'd say, all right, for 129, and just assume that we have significantly more bits for now. But I have 13 minus 129 mod 13, and that's mod 7. So that's the first equation here. And that gives me 1. So we've updated that bit to 1. And then K2 is 3 plus 5x mod 7. So that gives us 4. So now these bits have been updated. For 479, I do those same things and it becomes 2 and 4. So one of the benefits here is that 4 doesn't have to change. All we have to do is just look up both of the hash functions to be able to determine whether or not we can say that something is there. Then if I do 129, I would check and both of them would be positive. And now with 123, that first function returns 0. So 0 and 2, one of them passes, but the other one doesn't. And so in this case, we know for a fact that 123 is not in the Bloom filter. It will never produce a false negative, but it can produce false positives. And so intuitively, what we can see is we add more bits and more hash functions, we gain more accuracy. So that the key thing is, what is the customer willing to do in terms of accuracy? And then you can say, well, I can calculate a Bloom filter. We put in all these URLs to store in, and we can just run the program and gain our accuracy there. And so I've been alluding to this idea of Bloom filter. Marty Rose is currently a senior software engineer at Google, and he worked on a project with Bloom filter. And so this is where this idea of using malicious URLs comes from. So they had to count a unique number of cookies, and they had to increment how many times a specific website had been visited. And basically, if they looked it up and it was there, they would increment a counter. So they would have some sort of array with all the URLs and a counter. Or they had a counter to check to see if all the URLs in this database, if they found them. So you would increment a counter. The logo isn't perfect because we now know why it's not perfect because it's a heuristic. It still gave very accurate numbers while also being very memorable. And so, so he said it's okay for me to share his LinkedIn and his email. So if you ever want to contact him about what it's like to work at Google, please feel free. So what I'd like to show you for the last minute is how it, okay, so this is 11:14, so I might have to start a little more on Friday's lecture. But what I have in code here is I've taken all the links from nendy.edu and und.com, so the main Notre Dame page and athletics. And I want to be able to determine them within 94.75% accuracy and see if it's if it's part of a Notre Dame website. So here what I did is I added them all up. And so what I've done is I've say 96.75, I've subtracted it. That gives me 0.0625. And I plug that into log base 2, that gives me 4 hash functions. And then I do 4 hash functions times 234 plus 105 plus 18,788, and that gives me 19,127. I put that in there and I have 110,377. You see that? And on the next slide, I compare, so the average URL length was 65 characters, so 65 times 8. And so with 110,000 approximately, that's about 65 URLs. So to solve this problem, and the code's available, and I'll dismiss you in a moment since I know it's 11:15. But what we're able to do with this hash function and using this idea of bitsets is we were able to reduce the memory from 19,127 URLs on average to 65. I'm sorry, with 212, my apologies, because it's 65 bits on average. So you see the significant reduction in memory there with a small trade-off in accuracy. All right, so does anybody have any questions about Bloom filters or anything else I've covered in lecture today? All right, so on that note, it's 11:15, you are dismissed. I will see you on Friday.